This is the tropical map discussion at the University at Albany on November 15th, 2019. I have a small audience in the room with me today and will occasionally interact with them. So we begin with the large-scale background conditions around the world. The sea surface temperature map shows something actually quite extraordinary, different from any other time in the record. We've highlighted in the last few weeks the Indian Ocean dipole. And we have a situation now where the Western Indian Ocean is almost as warm as that region near the date line where we have a Central Pacific El Nino structure going on right now. It's extraordinary to see the Western Indian Ocean this warm, so warm that it's favoring deep convection in this region. The general structure of the Indian Ocean dipole in its positive phase like this is to have enhanced trade winds going this way, which upwell cold water from the coast of these islands. And there's also a wind evaporation feedback in this region that is lowering the sea surface temperature here. This region of the world historically has had relatively shallow thermoclines, so that in MJO events, especially decades ago, crossing the region, they're able to mix up substantial cold water and reduce the sea surface temperature in the region as they go by, which has changed the behavior of MJO events crossing that region, because the thermocline here has been unusually deep. But now certainly with these strong easterlies, the thermocline here would be more like what you see in the East Pacific region. This event is so strong that it has realigned the overall ocean structure, and it's putting the system in an uncharted territory. And there's no trend in the Indian Ocean dipole. It's not clear why climate change would induce something like this. But nevertheless, this is the biggest event in the whole record. And if this cold east and warm west can be maintained, typically the Indian Ocean dipole fails across November and December in the ocean. Sometimes the convection keeps going and then results in a reversal of the Indian Ocean dipole sea surface temperature signal the following fall, because the convection interacting with the ocean during the spring and northern summer reduces the total sea surface temperature and results in a cold signal over here, and then a warm signal develops over here. So this is why the Indian Ocean dipole has this kind of biennial, so a two-year cycle associated with it, outside of its normal association with El Nino. Typically, the El Nino base state favors a wind stress pattern that enhances this Indian Ocean dipole structure. Part of the reason is that the Indian monsoon during the northern summer is weaker during El Nino events, because the El Nino event produces a Rossby wave train that then influences the wind state over here, suppresses the intensity of the monsoon, which means that the low-level winds over here are weaker during the summer and early fall, which results in less upwelling here and less wind evaporation feedback, and so the sea surface temperature comes up during an El Nino monsoon season, so that by the time the fall begins, it's anomalously warmer here, which engages convection in this region and amplifies easterly wind, when normally in the fall on the equator in this region the winds are westerly. There's a low-level wind, equatorial wind maximum in October, or roughly in the fall. But in an Indian Ocean dipole scenario, the westerlies typically weaken. In this case, the signal is so strong, we've got absolute easterlies in the region standing out even above MJO events that are going around the world. Now, this is the total sea surface temperature. Beyond the Indian Ocean dipole structure, there's clearly a warm signal in the western and central Pacific. It's absolutely warm, and it's also anomalously warm. So here's the sea surface temperature anomaly pattern. Again, an extraordinary dipole structure in the Indian Ocean. I doubt that anyone can look at this and suggest, like some of our earlier peer reviewers had said, that the Indian Ocean dipole doesn't exist independent of noise. This is a robust pattern, and the Pacific along the equator here shows warmth now in places all the way along to the coast of South America, but not meridionally broad. The cold tongue is weaker than usual, and it's anomalously warm near the dateline, but this anomalous warmth just west of the dateline is the controlling factor in the flow, because if this region were not anomalously warm, this region over here would be absolutely warm because of its warm anomaly, which would result in convection developing here, but there hasn't been much convection in the eastern equatorial Pacific. The principal reason is that a warm anomaly back here means absolute warmth. Normally in an El Nino event, the West Pacific cools enough. This becomes anomalously cool that while this is anomalously warm, the absolute sea surface temperature maximum can sit near or east of the dateline. But here the sea surface temperature maximum is still shifted a little bit to the west. So the absolute temperature again is highest in that region just east of New Guinea extending to the dateline, not points eastward. So here's some comparable previous years in terms of the Indian Ocean dipole. What I've done is taken October 2019 and subtracted October 1997. You can see, of course, in 1997 there was an amazing intense El Nino event. So we see these cold in 2019 relative to 1997, but the warmth west of the dateline is it's much warmer in 2019 west of the dateline, which implies absolute warmth over here. Now the Indian Ocean in 1997 had a pronounced dipole, but it's actually anomalously colder in the present event here, but it's anomalously warmer over much of the Indian Ocean now. And part of this may be associated with a long-term trend in the Indian Ocean. But the principal difference that has the Indian Ocean dipole stronger right now than it was in 1997 is this region right here and this region right here, producing a net contrast in temperature relative to 1997. Another Indian Ocean dipole event in the past was 1994, but this one is even stronger than that. You'll notice the East Pacific here maybe is warmer in places now, cooler in others. It's kind of nondescript in the East Pacific, but again, warmer West Pacific this year than in 1994, but cooler now in this area here and warmer now here. And again, there's a relative contrast showing that this event, this Indian Ocean dipole event, is stronger than these other events we're looking at. And over the entire record, the Indian Ocean dipole signal this year is the strongest ever observed. It's useful, I think, if I can find, I think in this data, on this Ezra website, you can find the recent circulation patterns. And I was looking at 200 millibar heights, And I want to just go back 90 days. The outgoing long-wave radiation signal has been active over the Western Indian Ocean for many months, even going back through the summertime. But this is the geopotential height pattern for the last 90 days, and I'm not really seeing any kind of extraordinary geopotential signal emerging from the Indian Ocean. These anomalies are small. If I were looking at a comparison against 1997 El Nino signals, for example, big El Nino signals, you would see a wave train here with substantially greater amplitude than what we're seeing here. The Indian Ocean dipole is extraordinarily strong in the sea surface temperature pattern, but it's not producing a large-scale pattern of mass divergence back here that's controlling the large-scale flow. I'll show you, though, the lower tropospheric, maybe I'll show that to you now. The lower tropospheric wind associated with the Indian Ocean dipole signal is very strong. So there's the enhancement of the trade winds, but when you look in the upper troposphere, there's a little bit of a signal, divergent signal over Africa, very far western Indian Ocean. If you go back over a very long period of time, though, you go back through the summer, there really doesn't seem to be anything extraordinary. It's more like dominated by the upper tropospheric velocity potential pattern is dominated by these subseasonal signals coming around, not by something that is as stationary. See, even August and September, we had a substantial convective signal over the Indian Ocean and not really very much right there. But just recently, a velocity potential over Africa has emerged. It's interesting. Why would it be placed there as opposed to the western Indian Ocean, where the warmest water is located? I don't think that we really have a full understanding of how the Indian Ocean dipole couples into the global atmospheric circulation signal. And there really hasn't been a whole lot of study on that. And most of the time it only matters in, say, October and November. But perhaps if events like this like the present one can occur, it's possible that in the future we have other events like these. It would pay to understand the dynamics of coupling between the Indian Ocean dipole and the large-scale circulation. That's right, and there really isn't. Going back, let's see. Finding where my data files were. This one. So I mean, you do see ridges way back here, but they're very high latitude. Yeah, this is 90 days. So if I meant 90 days anyway. If I can go to reanalysis, 90 days. That's what we're showing. If I shorten to just 1 month, then the recent MJO event is going to stand out. And in that case, you see a big ridge over here, but a trough over Arabia, which is interesting. It's not exactly what I would have expected if there was a large convective forcing and mass divergence pattern over the western equatorial Indian Ocean. It's not really showing up as clearly as one might have expected. I did see one diagram of divergent wind just for one 1 week period back in October, when the MJO happened to be over the western Indian Ocean, that showed a beautiful wave train extending out of the Arabian Sea region and across the world. But it was not, it's not a a long-term signal that I think is actually coupled to or dominated by the Indian Ocean dipole, or we would have seen it in the mean state. So why then are the circulation signals associated with the Indian Ocean dipole appearing to be so much more rotational than divergent? Because that seems to be what's going on here. MJO timescale things are more divergent. Even ENSO is less divergent than MJO things, but fundamentally the MJO in the upper troposphere is a Kelvin wave, which by definition is divergent. And so it would show up in the velocity potential more strongly. But the pathway whereby the lower frequency signals tend to associate with the large scale flow is more rotational. More Rossby wave features rather than Kelvin-like features. So if it were like a Kelvin wave, more so it would radiate away. I mean, you might expect a gill type structure to appear, but we're not really seeing that. And I'm not sure I understand why. I mean, maybe the intensity of the convection over the Western Indian Ocean just isn't that great associated with these signals. Yeah. So here's the OLR signal. This is from the 5 north to 5 south filtered OLR anomalies from the CPC. And I mean, the convection has been going over the Western Indian Ocean, but the periods of intense convection over here are associated with the eastward moving events. And it's superimposed on this low-grade convective signal. So it doesn't really appear to me like there's a static kind of low-frequency convective signal that is appreciable in amplitude in comparison with what is achieved when these subseasonal things go by. And I mean, for what it's worth, looking back over the late spring and into the summer, there was a Central Pacific convective anomaly. And of course, the strongest signals are going to be when the subseasonal signals are superimposed on it. But looking back in the past, I'm going to show Hofmüller diagram for 1997, just so you can get a comparison of what a really strong low-frequency forcing signal looks like. So I'll zoom out here so that we can kind of see the whole picture first. This is longitude and time over the whole year of 1997. And you can see the shading is active convection suggested in the blue and suppressed convection in the warm colors. So in 1997, there was a big MJO event in February-March that basically kicked off the oceanic Kelvin wave you can see right here in the blue contours, that then amplified the El Nino event going forward. But as the El Nino event grew, the large-scale structure associated with it included Western Indian Ocean active convection, and you can see in the fall pretty substantial emergence of an Western Indian Ocean convective signal. But if you smoothed over this period, the actual amplitude of the OLR anomalies associated with it are not really very strong. The times when the convection over the Western Indian Ocean was substantial was when the higher frequency convectively coupled waves were crossing the region. And so you would have seen emergence of Rossby waves moving around the world from this event, and this event, and this event, and that event. But overall, there might not have been very much of a signature, whereas you go over here in the Pacific region at the same time, the scale of the big kind of subseasonal convective events broader in space and in time than the ones you see over here. Everything is more intense over the Pacific Ocean. Another event we already talked about was 1994. 1994 is more similar to the present El Nino signal than 1997 is, but Indian Ocean, you see active Western Indian Ocean convection, Pacific convection, but overall the scale of the convection, including the higher frequency and the low frequency signals together, convection is quite a bit stronger over the Pacific than it is over the Indian Ocean. The mean state convection here is not as strong as the mean state convection over here. But it seems as though we don't get as much of a large-scale response to Indian Ocean dipoles, even in proportion to the intensity of the OLR as we see associated with the Pacific. So I think there's a lot of room for research in understanding how the Indian Ocean dipole signal couples to the large-scale circulation. So I don't think that this is really broadly understood. So I'm going to go to the tau buoy data now and look at cross-sections of what's been going on in the Pacific Ocean. So this is from back pentad ending on November 3rd. Cross-equatorial average total, ocean temperature here, and subsurface anomalies here, the anomalous pattern on the bottom. And we're seeing an eastward shifted warm pool, but with the absolute warmest water in the farthest west regions. And that's not the usual configuration for a major El Nino pattern. I'll give you an example from 1997 at the same time. 1997, October, yeah, this will be good, October 20th, 1997. And we'll bring up the diagram just so you can have a relative sense of just how this structure in the Pacific is different. So obviously the anomalous pattern is wildly different, but presently the absolute warmest water is here. In 1997, the absolute warmest water is cooler than the present warmest water, but it shifted well to the east, and so the sea surface temperature maximum is actually east of the dateline. So given that it's anomalously cool, or it's colder than climatology in the west, whereas now it's warmer, it's presently anomalously warm in the east, but the scale, let's go, I'm going to show this is the most recent pentad for comparison, and so we can compare the two signatures. It's not surprising, even though the sea surface temperatures of the East Pacific and the subsurface temperatures of the East Pacific are quite warm, they're less than half the amplitude achieved in 1997, and they are occurring at the same time that the West Pacific is anomalously warm, not cool. And so given that the West Pacific is anomalously warm and is absolutely warmer than any temperature in the Pacific at the time in 1997, this is the region that we need to be watching for as the source, Rossby wave source, or the region for convection over the next few months. Until this region becomes anomalously cool, it's quite difficult for strong positive sea surface temperature anomalies to maintain here. Because what happens, it's anomalously warm, but it's not raining here. So the full Bjerknes feedback, coupling to convection that help to amplify the wind signal associated with El Nino, will not maintain the westerly anomalies in the region, and instead the westerly anomalies are episodic and purely driven by the subseasonal signals crossing by. So the result is that the ocean will keep getting hammered by westerly wind events, followed by trade wind surges, and the ocean will warm in the East Pacific and then cool and then warm and then cool, and they'll alternate like this instead of achieving a stable signature. Now, if we have a large West Pacific convective event with substantial westerly winds, it's possible that that whole pattern, the warm center of everything, could be advected eastward and achieve a full transition in the warm pool toward a more canonical El Nino event. If that kind of event doesn't occur, the warm water volume in the West Pacific isn't depleted, and so we could get East Pacific cooling and back to a neutral or weak La Nina state, but then there's still risk that a large westerly wind event can put the system back into an El Nino condition over a few months. So this is not a stable configuration for a season. It makes it difficult to make long-range predictions about where ENSO is going to go. So let's take a look at some of the other. This is November 3rd, November 13th. There's been a recent surge in the trade winds that's now been replaced by anomalous westerly winds. You can see that in the diagram I showed you here earlier. There's the surge in the trade winds right there. This is an MJO event, the easterly phase of an MJO event moving around the world. The westerly phase of the MJO came across the Indian Ocean, couldn't couple to convection very well, and so moved rapidly out to the West Pacific. Out here it produced another substantial westerly wind event, and this whole thing is now driving a downwelling Kelvin wave development, which we'll be seeing, but this thing doesn't stay long. It propagates back around the world. It's crossing the Western Hemisphere in the first week of the ECMWF forecast. There seems to be a westward moving wave in here, perhaps a Rossby wave, that's propagating some of these westerly wind anomalies back to the west again. There seems to be perhaps a low frequency westerly wind signal that's developing in the Pacific that would be coupling to the West Pacific and Central Pacific warm anomaly, but it's not sufficient, to my guess, to solidify an East Pacific warm signal that would, and a substantial cooling of the West Pacific that's enough to make the West Pacific net cold while the East Pacific is net warm, so that the whole thing shifts to a more canonical ENSO state. You'll notice coming behind the westerly phase, you've got the easterly phase, comes around, comes back, this comes around the world, comes back in here, and this easterly phase is now intersecting with the Indian Ocean dipole signal and producing what could be one of the most extraordinary trade wind events in the Indian Ocean ever observed. I haven't compared against the full climatology, but it's possible that the strongest easterlies this time of the year ever observed there are achieved with this superposition of the Indian Ocean dipole and the MJO.
Do you think that MJO is going to get caught up in the early phases and possibly lead to like a cold signal here in eastern U.S.?
So the question is, does the MJO signal come along, hang up here? And it's hard to say because the index will certainly hang up. The question is whether the propagating component of this, because the Indian Ocean dipole signal here, the full intensity of the wind seems to be stronger than it was before, and we remove a 120-day time mean to make the RMM index, and that isn't sufficiently representing the low frequency signal. So the low frequency signal presently being stronger than that is going to project onto the RMM index and hold the signal in this region, whether the MJO stays there or not. What happened the last time was MJO signal comes across this region and doesn't really stall out and slow down. like it often does when the Indian Ocean is broadly warm. You see, in order to develop a slow MJO signal in this region of the world, you need upper tropospheric easterly wind. Lower tropospheric winds can be close to zero or westerly, but the MJO induces a trade wind surge that advects moisture from east to west. Well, this is what the main argument is. I think some of Ahmed's results would disagree in terms of how important this signal actually is, because it turns out that the western Indian Ocean is where the strongest gradient in the late summer and into the fall is where the strongest zonal gradient of moisture is. But it's not necessarily right where the convection with the MJO begins. It can begin there or farther east. But whether the convection begins there or not, the precursor to the MJO convection is a surge in the trade winds. And if there's a gradient of moisture over the western Indian Ocean because of the background winds along Africa intruding dry air from the extratropics, the MJO signal coming into the MJO circulation signal coming into the region is going to make the western Indian Ocean more moist, because if there's a gradient that points eastward and you get easterlies on it, the place will moisten, the region will moisten. But that's a consequence of the MJO circulation signal coming into the region. It's not necessarily a cause. I mean, obviously, if the MJO convection begins there, it can only begin there because it's moist. And it becomes moist because of the advection. But it's not necessary for the MJO to begin in the region where advection is important, because the MJO convection can begin farther east where there's no real moisture gradients. So the advection is not really relevant to increasing moisture at all. It's just using the mean state moisture in the environment. And the MJO doesn't have to have an anomalously moist signal really to get going in that sense. It just needs moisture. So the index may hang up, but I think that the actual MJO signal is going to move through fairly rapidly. Another complicating factor in the index, though, is that Rossby waves also project onto the index. And we've got something coming back to the west here at the same time the surge in the trade winds coming around the world would come back to the Pacific. So you can see it coming in here, rapidly eastward moving, easterly wind anomalies in the eastern basin, but it's being interfered with by this westward moving westerly signal, which basically keeps the westerly phase going longer in the western Pacific than it would have gone if the MJO were the only thing that mattered. So this makes for an interesting superposition going forward. It's interfering with the upcoming Pacific trade wind surge, which might positively project toward warming in ENSO. Question is then, the next time around, does a strong easterly phase of a Rossby wave then interfere with the eastward moving westerly phase of the MJO when it comes back into the region? It's an interesting structure anyway. The interplay between the evolving low frequency pattern and the subseasonal condition. You can see by the amount of washout of the low frequency easterlies here when the MJO westerlies came through. Other than this is the cyclone. What was its name? It was in the Arabian Sea. So there was a wave associated with that, the cyclone easterlies here. The MJO cuts through, and on the large scale, it's bigger. The MJO amplitude has to be stronger than the IOD amplitude in the wind in order for the MJO signal to reverse the sign of the IOD, of the total wind. So if the total wind becomes westerly, then it means that the amplitude of the subseasonal thing coming through is stronger than the amplitude of the IOD signal. But you're not really seeing a continuous propagation here. It flares. This actually isn't different from the way most MJO events behave, although the location of this signature is perhaps different, because what happens is in velocity potential, I can maybe come up here, there you sometimes see a continuous propagating signal with the MJO. Maybe over here we're seeing something that's continuous, but it's also highly episodic, coming in local bursts that don't really have clear precursors in the zonal direction in the tropics, say to the west. There's an overall envelope crossing this area, but each one of these bursts are bursts of divergence that are driven by the breaking waves from the extratropics. So a breaking wave from the extratropics can induce mass convergence or mass divergence into and out of the tropics, which control these large amplifications of the signal as it moves around the world. And sometimes there's a train of these things that just move all the way around, come back. That is a component of what I think dominates the physics of the MJO. Checking the time. Okay. So here's the global satellite imagery, infrared satellite imagery, showing where it's raining presently. Notice even though the East Pacific is warm, it's not really raining in this area. Convection is not occurring in that area. It's occurring back here where it's anomalously warm. We've got a cyclone here. The Indian Ocean has active convection in the western regions associated with the Indian Ocean dipole. It's relatively dry here. Of course, the Amazon signal is ever present and moving south this time of the year. In longitude time, we looked at this briefly before. We saw the ENSO signal in the summer, but now very little convection going from near the dateline east. And the strongest signal seems to be suppressed convection near the maritime continent, which is an ENSO and Indian Ocean dipole both signature. It's hard to separate the Indian Ocean dipole statistically from ENSO in its impacts because they tend to occur together, and the sample size of events when they are opposite the normal is really small, and so in an individual month it's then hard to separate what's driven by subseasonal signals more than low frequency and what's ENSO and what's IOD. But we've been seeing these MJO or Kelvin, atmospheric Kelvin and MJO convective events moving eastward across the region there, and quite an amplification going on right now. The active signal crossing the western Indian Ocean, weakening the suppressed convection here. You'll notice that the amplification effect coming across here is larger, and the subseasonal component of the western Indian Ocean is larger than the low frequency western Indian Ocean signal. But the suppressed convective signal near the maritime continent is larger in the low frequency than in the subseasonal. A subseasonal signal crossing here is not able to reverse the sign. And then it arrives over the western Indian Ocean, and we get our westerly wind event going recently. That's this one. So here's the MJO signal coming around, Rossby wave signal coming back. MJO signal will be coming in here. I think we're starting to see the next MJO westerly phase just starting to erode the easterlies here again coming around. But think about the time scale that implies. this is 15 days here, and then you go back another 10. So it's the subseasonal signal right now seems to be dominated by signals shorter than 30 days. This makes it more difficult to use the MJO to make predictions out in the weeks 3 to 4 range, because because noise associated with other variability and the amplitude of shorter time scale signals within it mean that there's less to work with statistically going out at those kinds of lead times. I want to take us back and look at the behavior of the RMM index and how it's behaving in the models. So we go to MJO, and we come down to the dynamical forecasts. And we've actually had a pretty substantial event coming around the world with an amplitude up to 2 standard deviations, maybe sometimes in a little excess of 2 standard deviations. You'll notice the previous signal, it stalls out over the Western Indian Ocean, which is what the model seems to be doing with it. This particular model, this is the Jeffs, brings the signal back around, just kind of sticks around the Western Indian Ocean. The previous event did stick around there for a while. Eventually it escaped, lost amplitude in the net, crossing the Eastern Indian Ocean, and this is in part what you'd expect because there is a static signal over here with the IOD that's not completely being subtracted, which is moving everything this direction on the diagram, but also the signal with the MJO is actually weakening its convection as it crosses that region because of the forced large-scale subsidence there. But there was a big amplification across the maritime continent region. Now, don't let that fool you that the convection was growing over the maritime continent, because it wasn't. It's quite dry in that part of the world right now. This amplification is circulation induced, and the RMM index is dominated by the zonal wind. So there's this amplification here, signal comes around the world. Now look at how long it spends in the different phases. So there's only 2 days, maybe 3 days in each of these phases, which this is half the normal phase speed that we would expect for a canonical MJO signal with a 40 to 50 day time scale, and that's consistent with what we were seeing in the Hofmüller diagrams earlier, that the time scale seems to be maybe 20 to 30 days right now, probably right around 25 days. So the amount of time it takes to go around the world and back, this is just a 15-day loop right here, but it comes out and sticks. But now look at what the other models do. So this is ECMWF, and it's got a loop that's coming around. There's probably a large-scale signal that's coming all the way around the world, forced by Rossby wave breaking, Rossby wave dispersion, and Kelvin wave propagation. There's a very large ensemble spread at the end of this period, so suggesting large uncertainty in the phase speed of the signal coming around the world. So that in the model, when you go out to week 2, a lot of the subseasonal signal is washed out. So you think of ensemble averaging is diminishing the net, the signal that you would see associated with the MJO, which would imply that the signal that's being left behind is going to be largely low frequency. So whatever the base state is looking like in weeks 2 and 3 is what you're going to see out of the models in those time frames. European Center climate model has that. It comes out, goes back. That's similar to what ECMWF ensembles are doing. Shifted down a little bit. To the right is bias correction. This is bias correction here. They bias correct the data fields and reconstruct the index from the bias corrected fields rather than bias correcting the index. And that would suggest more Pacific signal is likely based on recent months' differences between the fields. And here is the climate model again, similar shift up to the right, but overall the story is similar. Signal comes in, does a loop back to the Indian Ocean, and then you've got a few ensemble members that come back out to the Pacific in this time frame. I doubt that there is a lot of skill in this long-range prediction, and again, if you looked at the endpoints of each of these ensemble members a month out, they're spread all the way around the thing. And so it's going to have a lot of ensemble washout in the model forecast.
Can you explain again the bias correction?
Yeah, so what they're doing is comparing the data fields for the OLR U850 and U200 against the recent model errors. So it's a window going back. I don't know exactly how long. It's some recent months period dominated by the recent weeks, so that if the model bias in the field during that time was in a certain direction, that's what they're subtracting out of the fields today. It would be better if they used a climatological bias from a reforecast climatology. But the recent errors do have a correlation with those with biases calculated that way. So this is a cheaper way of getting at the bias. And so it works. It's overall an improvement, but it's not the same as what you would get, for example, if you corrected the index itself, or if you used the full climatology of model hindcasts.
And the F and M, which one is corrected?
So M is corrected.
Okay.
So this is the bias corrected version here. This is the original. Sometimes I get some insight for these in my long range forecast opportunities when recent weeks have confirmed the general movement like this in this direction. I can look at the model fields and say, well, the model has too much phases 8 and 1, and so I can go to my seasonal regression maps for what phases 8 and 1 look like and subtract some of that signal from the ECMWF forecasts and end up getting a bit of a bias adjustment in the fields. But given that this bias adjustment is made by bias correcting the fields in the first place, it might be nicer if they eliminated the middleman and just gave us the bias corrected fields from the model, and so we could plot the map and then see what the difference is in the fields themselves. But still, there's some insight that can be gained from comparing these and comparing the model forecast maps, so 500 millibar geopotential heights against the MJO regressed climatologies for the same time of the year, and then move the circulation, say at the end of week 2, toward the solution that the correction puts back in. You see this loop right here. This kind of thing frequently occurs when the MJO is intersecting with higher frequency waves. Can be induced by intersection with a Rossby wave signal, so that what we're seeing over the Pacific right now. So it's like we've got a Rossby wave that's moving westerly, low-level westerlies toward phase 7 in week 2, so you see that right here, which projects the index in this direction in that time frame, and then that disappears and comes back out, so then it starts following the original convective signal. So I think I'm getting close to running out of time. Bottom line right now seems to be that there remains a substantial subseasonal signal that we should be accounting for, but its behavior is not really well represented by the RMM index. We're getting interference with the Rossby wave that's influencing the character of the RMM signal coming around the world. That Rossby wave may be relevant to the large-scale signal in the extratropical circulation, but that doesn't necessarily mean that the Rossby wave-induced signal in the RMM index is associated with the same response patterns as as an MJO signal dominating the RMM index would be in that time frame. But overall, the signal comes back around the world, and probably late December timeframe, we'll be seeing active convection over the West Pacific again. So I think that's good for today. We'll get ready for the tropical lunch group. Cool. I have to